There is a structure in northeastern Wyoming. It is 867 feet tall. At its base, the diameter is roughly 1,000 feet. At the top, 275 feet. The sides are not smooth. They are composed of long, straight columns. Each column is roughly hexagonal. The columns run vertically, parallel to each other, from near the base to the top. The columns average between 6 and 8 feet across. Some measure up to 10 feet. The top is flat. The summit plateau is level across its full 1.5 acres. The surrounding terrain is sedimentary. Rolling hills, limestone, sandstone, eroded over millions of years. Devil's Tower is not made of any of those materials. It is phonolite porphyry, a type of igneous rock, intrusive, meaning it cooled underground. At the base, there is a debris field, chunks of the same columnar rock, fallen sections, scattered around the circumference. The first formal survey of Devil's Tower was conducted in 1875. The surveying team noted the columns, the flat top, and the debris field. Columns, flat top, debris. Those three things have been consistent in every survey since. That is the object. That is where we start. The US Geological Survey has a clear explanation for Devil's Tower. Roughly 50 million years ago, magma from deep underground was forced upward. It pushed into the sedimentary rock above it, but did not break through to the surface. It cooled slowly inside the earth. As it cooled, it contracted. The contraction created fracture lines. Those fracture lines followed the geometry of thermal stress. The result was the columnar jointing visible on the surface today. Over tens of millions of years, the softer sedimentary rock surrounding the formation eroded. The harder igneous core remained. What you see now is what was once underground, exposed by erosion. This explanation was formalized in the early 20th century. It has been the accepted scientific position for over 100 years. There are other examples of columnar jointing worldwide. The Giant's Causeway in Northern Ireland, Fingal's Cave in Scotland, Svartifoss in Iceland. The geological process is well documented. The mechanism is real. The physics are sound. The explanation accounts for the columns. It accounts for the igneous composition. There are two things it does not fully account for. The first is the top, a volcanic plug cooling underground and then exposed by erosion over 50 million years would be expected to have an irregular upper surface. The top of a magma intrusion is not a planned geometry. It would follow the pressure contours of the surrounding rock. It would be uneven, bulging in places, fractured at different depths. The summit of Devil's Tower is 1.5 acres. According to USGS survey data, the elevation variation across that plateau is less than 10 feet. That is a surface more level than most poured concrete floors. The second is the debris. At the base of Devil's Tower, there is a continuous ring of debris. These are sections of the same columnar rock. They have fallen from the walls. Erosion, freeze-thaw cycles, gravity. That is the standard explanation for the debris. But the fallen sections are not random fragments. They are clean cross-sections. The breakpoints are at the joints between columns, not through them. The columns themselves stand between 15 and 20 feet per visible section, stacked vertically. The debris matches the wall. Now, both of those observations, the flat top and the uniform debris, are acknowledged in the geological literature. Neither is hidden. The USGS notes the level summit. Researchers have documented the debris field extensively. What the literature does not discuss in detail is what the structure looks like when you describe it without using the word geological. It is a vertical cylinder, approximately 1,000 feet in diameter at the base, slightly narrower at the top. The surface is divided into parallel columns. The top is flat. That is also a description of a tree stump. The similarity in form has been noted in online discussions. It is not a new observation. It is not taken seriously in peer-reviewed geology. But the form is what it is. Columnar jointing in igneous rock produces hexagonal columns. Cellular structure in mature tree trunks also tends toward hexagonal geometry. This is a convergence in form, not evidence of anything. Hexagons are common in nature. Cooling stress produces them. Biological cell packing produces them. The visual overlap is exact. Devil's Tower sits on the Belforche River. The surrounding rock is Triassic and Jurassic sedimentary, gypsum spring deposits, spearfish formation, red beds. Those formations were laid down in shallow marine and floodplain environments between 250 and 150 million years ago, before flowering plants, before modern trees. The official geological explanation places the igneous intrusion at 50 million years ago. The Eocene, that is after flowering plants, that is recent, geologically, but the surrounding sedimentary rock is much older. The exact age of the intrusion is debated in the literature. Potassium-argon dating has produced a range, 40.4 million years, 52.5 million years. The estimates vary by study. The gap in the explanation is not about the columns. The columns are explained. The gap is about the top. A magma intrusion that cooled underground, surrounded by sedimentary rock on all sides, and then exposed over tens of millions of years of erosion, does not produce a flat top as a default outcome. The surrounding rock eroded unevenly. That is what erosion does. The top of Devil's Tower did not erode unevenly. That question is in the literature, in the margins. It has not been answered directly. In central Utah, there is a geological feature called the San Rafael Swell. It covers roughly 2,400 square miles. The surface is composed of uplifted Jurassic and Triassic sedimentary rock. Within the swell and the broader Colorado Plateau, there are hundreds of isolated buttes and mesas. The term mesa is Spanish for table. The flat top is the defining characteristic. The standard geological explanation for mesas on the Colorado Plateau is straightforward. They are remnants of a formerly continuous plateau. Erosion cut away the surrounding material. A hard caprock layer on top resisted erosion longer than the softer rock below. What remains is a table of the original surface. This explanation is geologically sound. It applies to many formations on the Colorado Plateau. Monument Valley is composed of West Mitten Butte, East Mitten Butte, Merrick Butte, and others. The visible red sandstone is Permian Decelli sandstone. Below that, Organ Rock shale. Above, a thin cap of harder rock. The walls are nearly vertical, in some cases completely vertical. The shape is a cylinder with vertical walls, a flat top, and debris at the base. The forms are not identical. The Monument Valley formations are sedimentary. Devil's Tower is igneous. They formed through different mechanisms. The Monument Valley formations show horizontal banding, sedimentary layers deposited over time. Devil's Tower shows vertical columns, no horizontal banding. That convergence in form across two different geological classifications is in the record. It has been noted by researchers studying geomorphology. The distance between Devil's Tower and Monument Valley is roughly 600 miles. The question the geomorphologists are asking is about process, about persistence of form, about why vertical becomes the default wall angle and flat becomes the default summit geometry. The answer in the standard literature is caprock and differential erosion. That is the answer. But it does not explain why the caprock is consistently gone. On most of these formations, the hard caprock layer is absent or nearly absent on the summit. The surface is exposed, with no protective layer remaining above it. Harney Peak is the highest point east of the Rocky Mountains. It is composed of Precambrian granite, roughly 1.7 billion years old. The summit is granite spire formations, not columnar in the same way as Devil's Tower, but the surrounding Black Hills terrain shows a consistent pattern. The Black Hills are a geological dome. The core is the oldest rock. Concentric rings of progressively younger sedimentary rock surround it. Erosion has exposed the core. Courthouse Rock is a butte in western Nebraska. It rises 400 feet above the surrounding plain. The top is flat. The walls are nearly vertical. It was a landmark on the Oregon Trail. Emigrants noted it in journals from the 1840s. Adjacent to it is Jail Rock. Same composition, same profile. Two isolated, flat-topped structures standing together. These are 4 sites, different states, different rock types, different geological ages, different formation classifications: phonolite porphyry, Permian sandstone, Precambrian granite, Oligocene clay and sandstone. 4 different materials. 1 shared external form. There are more. The list is long. Shiprock, New Mexico. A volcanic neck, 1,583 feet tall, flat remnant summit, radiating dikes at the base. Square Butte, Montana. Igneous intrusion, flat summit, columnar basalt walls. Scotts Bluff, Nebraska. Sedimentary, flat top, vertical walls, debris slope at base. These formations are distributed across the interior of the North American continent, roughly between the 30th and 50th parallel, roughly between the 95th and 118th meridian. They are concentrated in the interior west, not the coasts, not the far north. The distribution is in the geological record. It has not been systematically analysed in terms of pattern. Individual formations are studied individually. The inventory as a pattern has not been the subject of a peer-reviewed study. We have been looking at individual objects. The debris at the base of Devil's Tower has been studied. The fallen sections are classified as rockfall from freeze-thaw weathering. That is a documented process. The sections that have fallen are intact column cross-sections, not shattered rock, not rubble. Intact geometric sections. If you stand at the base and look up, you are looking at columns that extend for several hundred feet without interruption. The joints between columns are tight. The geometry is consistent. This is well documented in every survey from 1875 to the present. For this structure to be the stump of a biological organism, one thing would need to be true. The organism would have to have been enormous. The diameter at the base is 1,000 feet. That is not a size that exists in any documented biological record. The largest known tree has a base diameter of 36 feet. Devil's Tower is 1,000. The hypothesis that these formations are biological in origin is not in the scientific literature. It circulates in amateur geology forums, in alternative history communities, on certain YouTube channels. It is not the position of any geological institution. But the form is what it is. What the official explanations account for is the material, the rock type, the cooling mechanism, the erosion process. What is not addressed with the same rigour is the geometry. The flat tops, the vertical walls, the debris that matches the walls, the distribution across a specific interior corridor. Every survey done on these structures begins with a question about what they are made of. The composition is known. The form is also known. The question that does not appear in the literature is a simple one. What process produces a flat top?